Okay, we're now going to do the second part of our lecture about the logarithm. It was going to go too long, so I decided to break it up into two pieces. And so in the first part, we proved, set some definition and proved a basic result. Let's prove another one. Okay, we'll start off. Say that if A is less than C is less than B, then L of AB is equal to L of AC plus L of CB. Okay, so otherwise this is not actually surprising, right? Because what we're doing, we're just breaking up the area under the curve into two pieces. We're just going through the process of showing that our way of capturing that does preserve that intuitive property. So we're going to first show, again, like we did in the previous result, or the last result from the first part of this lecture, show that L of AB is greater than or equal to L of AC plus L of CB, and then we'll flip that around and go the other way. So let's start off with let Q be a partition of AC and let R be a partition of CB. It's not difficult to see that if we take the union of Q and R, that will give us a partition of AB. Okay, so note that LP of AB is equal to LQ of AC plus LR of CB. Okay, a lot of letters there. Okay, but this sum is just equal to the sum of these two sums. Okay, and so from that, okay, it follows that L of AB is greater than or equal to this. Well, why? Well, L of AB is greater than or equal to LP of AB because it's the least upper bound, and this is equal to that. Okay, so there was nothing special about LQ or LR, and so it's not difficult to see from that L of AB is greater than or equal to L of AC and L of CB plus L of CB. All I have to do is let those vary, and this, okay, yeah. So, because my L of AB is fixed, and I can vary my LQ and LR. Okay. Now show that L of AB is less than or equal to L of AC plus L of CB. Well, LP of AB is less than or equal to those. How? Well, take a partition of AB, and we will construct partitions Q and R from it for A, C, and CB as follows. Okay, we'll first start with a special case. Suppose P is equal to AB, then we let Q be equal to AC, where we just add the point C, and let R be equal to CB, again just having the point C there. Then we have LQ is equal to, we can calculate it as being equal to 1 over C times C minus A. We can calculate L of R to be 1 over B times B minus C, so that LQ AC plus LR of CB minus LP of AB. And what am I doing here? I'm saying, okay, I want to show that my LQ, my sum is bigger than my single one. I subtract the single term from those, and I'm going to show it's positive. Okay, well, I just roll in the formulas here, and I do the arithmetic, and the only interesting thing I do on it is the first term. I trade in my C for a B to get something smaller here, and then I do the math on this, and this in fact turns out to be equal to 0, so this difference is greater than 0. And so it follows that my LQAC plus LR of CB is greater than or equal to LPAB in this case. Okay, having proved a special case, we'll now prove a general case. We may assume that C, the general case where we just let P be a partition, find the K that contains this point C. Okay. Let Q be everything up to just before that, and then add a C to it. And let R be C plus everything that falls after the C. And we take the difference. And here, what happens is LPAB has terms in common with LQ and with LR. And when we do this subtraction, the only terms that don't fall out are associated with the interval that contains the C. And this case then is just exactly the same as the special case we proved. So now take that and note that LP of AB has to be less than or equal to L of AC, L of CB. Since this is true for any P, we can see that LAB is less than LAC plus LCB. And again, by piecing things together, we've got this sum trapped between L of AB and L of AB, and so it's all equal through here. All right, having done our preparatory work, we can now define the natural logarithm. Let's give ourselves first, what if we have x greater than 1? Then we're going to define the natural log of x to be L of 1 minus x, or 1 comma x. And then if we have x between 0 and 1, we're going to let the natural log of x be negative of L of x to 1. Okay. We can now go ahead and do some basic results about the natural log of x. So if we have x greater than x and y greater than 0, the natural log of x plus the natural log of y is equal to the natural log of x times y. And so we case this out. I'm going to do one case and then kind of flip through the other pages so that you can look at them. But those of you who are enrolled in the class have the slides. It's just checking things. This is a lot of things to check. So the first special case we consider x, y greater than or equal to 1. Then 1 is less than or equal to x, less than or equal to x times y. So it follows that the natural log of x is equal to L of 1x, and this will be equal to L of 1x plus x, L of x and xy. That L of x, xy, we can factor out that since we have a common factor there, we can get rid of it. It gives us back to L1x, and so here I have Lxy equal to the natural log of x, natural log of y. And the rest of it is just, as I say, taking special cases. What if they're x and y are both less than 1, you work that out using these steps. A subcase, if x is less than 1 and y is greater than 1, then you work that out again, just being careful, taking your time, using these same properties that we proved about L. And again, in the case when x times y is less than 1, again, it's a subcase of a subcase of a subcase. I mean, so it's tedious, but it all works out. And so we can now assume and use all of these wonderful facts about natural log of x, having proved them.